I did manage to wreck a couple of patterns getting them out, which is the same value that we use in the 80 meter DC TOS QRP. So hopefully this will clean up the output on my... Happy to be back in the shack. It's a Saturday morning, the morning of the referendum in Australia. Hi folks, happy to be back in the shack. It's a Saturday morning, the morning of the referendum in Australia for an Aboriginal or Indigenous voice to Parliament. We're not going to go politics because ham radio is not about politics. It's about mucking around with radios. So today what we're going to do is we're going to check the spectral purity of all my QRP rigs, or most of my QRP rigs, and we're going to look at how clean or how dirty they are. So stick around. There are going to be some surprises, or maybe it's not surprising to you, having seen the way I build my gear. Well, what do we need to actually check spectral purity? Not so long ago, the main piece of equipment that's required, a spectrum analyzer, would have cost you thousands and thousands of dollars. But like I've said in previous videos, we live in exciting times where things that were once beyond the scope of the hobbyist have now become very, very affordable. And the spectrum analyzer is a piece of equipment that has become very available now and at a much cheaper price. And that's because of equipment like the tiny spectrum analyzer here. These are like $200 odd Australian. Not expensive at all, and I'll just show you what we have inside. I have seen people compare these to more expensive spectrum analyzers, and you know, spoiler alert, they're not going to be as good as a full-blown spectrum analyzer, but definitely accurate enough to make a good appraisal of spectral purity of a given device. So that is the screen on that. Lots of fun, and like I was saying, this sort of equipment that was, you know, in the realms of engineering workshops and whatnot were very, very expensive, has now become very affordable. Another thing which hams are playing around with a lot now is the nano VNA. So a VNA, vector network analyzer, once upon a time a very, very expensive piece of equipment. Now most hams, or a lot of hams, are using these as antenna analyzers, but they can do so much more than that. They can check for attenuation through filter networks and, you know, 1,000,001 other things that I've only just begun to scratch the surface of. So great piece of equipment, the Nano VNA. So I will be using my tiny spectrum analyzer with the SMA 10 watt 40 dB DC to 3 gigahertz attenuator. And basically what this does is it throttles back the power that I'm going to feed in here so I don't blow the tiny SA up. Now, those of you who've watched other videos on my channel will probably have seen the video where I attempted to check the spectral purity of my UV10R 2 meter and 70 centimeter hand talkie. Unfortunately, during that test, the radio blew up and I completely fried it. It did look like it was going to test okay, so that was a very interesting result. But now I have the opportunity to go HF. So we might just head off to the board and just look at some of the Australian regulations and the values that we're looking at to check to see whether the radio actually meets a requirement. This is the Radio Communications License Conditions Determination, or the LCD. That's what you'll see it referred to as for ACMA. And this is the spurious emissions limits for an amateur station. And for below 30 megahertz, as you can see there, we're dealing with 43 plus 10 log PEP dB and 50 dB. So whichever is the lessest. Now, there's a little bit of maths here, but it's not terribly difficult. There's a thing called the LCD, and that stands for License Condition Determination. It's an ACMA thing. And they are basically the things that we need to do as radio amateurs to stay within the regulations and the law. Now, the formula that we're using for frequencies that are less than 30 megahertz, i.e. HF, and below, is, it looks really complex, but trust me, it's not that complex. It's 43 plus 10 log, this is to the base 10, this log, PEP, which is peak envelope power. So putting Or that's number one. Or the other thing is just 50 dB. Whichever is the lesser. So if I pop in for the power 5 watts, which is QRP, it's what I'm normally using, you'll end up with an answer that is 49.9 dB, which is really handy because basically it's the same. So we're trying to get a dB difference between our fundamental and our harmonic. Now, some people say the fundamental and then first harmonic, and some people say that the fundamental is the first harmonic. I've heard all these arguments online. All you really need to know is the fundamental is the main frequency that you require, and then multiples across the spectrum of that frequency, you will see harmonics. Now, or you might see harmonics if they're large enough to measure. Ideally, you wouldn't see them at all, but most rigs, there will be something there, depending on how sensitive your equipment is. But I'm just going to quickly describe the idea of harmonics because a lot of you will know this, so you can fast forward. But some of you new hams might not understand how this all works, and it's quite a fundamental thing that's good to have a grasp of. Harmonics. Now, this is something that you'll probably have noticed that the ham bands tend to be multiples of each other. So you double 1.8 and you're getting up into the 3.6 megahertz range. You double 3.6 and you've got 7 and a bit. Double 7, you've got 14. Double 14, you've got 28. So you're going from 160 meters to 80 to 40 to 20. You can see that they're all multiples of each other. And this is very handy when you want to build antennas. And just remember that this all works except for the WARC bands, which are not harmonically related. So they're a little bit more problematic when it comes to building antennas and whatnot. But your more traditional ham bands that were around before the WARC bands, they are harmonically related. If you're looking at a spectrum analyzer, this down here is what's known as the frequency domain. And basically, it sounds really complex. Basically, you're going from a low frequency to a higher frequency. And you set that spectrum up to measure information that you require. And over here, oh God, there's so much junk on the floor here. Over here, you've got your dB. And you're normally measuring, say on this frequency spectrum here, you've got 3.5 megahertz. Just here. On the spectrum analyzer, when you hit transmit, you'll see a nice little spike. You might see some little spikes on the side. That's your 3.5 meg. And say that the top of that's at minus 10 dB. And then your first multiple of that, the harmonic you're going to come to after this fundamental frequency. So that is the fundamental. And then if we go up 3.5 megs, we come to 7 megahertz. Hopefully your 7 megahertz harmonic, you might call this the first harmonic or the second harmonic, depending on which camp you're in. But this harmonic is hopefully going to be a lot less than this one. So to make, if we're looking for a 50 dB difference, this would have to be at least minus 60 dB. Any less than that, we've got a problem. And then after your 7 megahertz, you're going to double it again, and you might have a 14 megahertz harmonic, and then a 28 megahertz harmonic. And none of these harmonics are allowed to be larger than a 50 dB difference. Now, if the filter's designed well, that's the usual relationship you're going to see, but don't count on it. A lot of the VHF and UHF rigs that are not filtered well, the Baofengs and whatnot, have harmonics that jump around. Some are higher, some are lower, and you might also have artifacts that shouldn't be there, that are not harmonics, that are also larger. Now, any spurious emission, be it a harmonic or a spur, needs to be less than 50 dB down in this case for HFs. If you find yourself looking at harmonics that are greater than that, you're going to have to arrange some filtering, and that's a fantastic opportunity to learn a little bit about how to build a filter. Quick note to any US hams that are watching this, FCC spectral purity requirements may vary, but I'm pretty sure they're close to what's required in Australia. And that's mainly because these regulations are based on ITU requirements. But check your local regulations. This is the OzQRP rig. We are going to be testing this rig. And the test setup, just so you know, is I have this attenuator. Now, the attenuator is just a way of throttling back the amount of signal that's entering the tiny SA. 10 watts, 40 dB from 0 to 3 gigahertz, presenting a 50 ohm load, and it all goes, just so you know, into the bottom port, the RF port of my calibrated tiny SA. So let's get us hooked up and get on 7.02 and get ready to key down. Folks, ready to key down. Let's have a look and see what happens. Thank you, Leon. As far as I can tell, apart from a few artifacts and whatnot popping up, that is clean as a whistle. Brilliant RF engineering. Now let's have a look at some less than brilliant, I am certain, RF engineering. This is my Mooncake transmitter. So I am feeling less than confident that this is going to be clean, but that's okay. We will fix it up if it isn't. So let's get this all hooked up. Let's get the power connected and see if we can get this to behave. It's on. Okay, but that's okay because the TS520 also has... The suspense is killing me. Now, we need to reset our spec for measurement because we're measuring harmonics, but we're measuring a harmonic of, let's say, 3.5 megahertz. Okay, folks, we have set this to 0 to 15 megs for 3.5, and and we've also obviously reset the frequency for the harmonic being measured. And let's just have a look and see what's happening. What an absolute mess. You're looking at about, for the harmonics that's being generated, first harmonics at minus 29. So 10 or 15, but just very, very messy as well. Spikes left, right, and center. And the harmonic that's being generated, delta 1 is minus 25 dB. So that difference between the fundamental and the first harmonic that we're dealing with is way too high. Not a big enough difference, 26. So about half of what it needs to be. Next rig to run the gauntlet is the QDX digital transceiver from QRP Labs. Absolutely love this little rig. FT8, all the digi modes, running through WSJTX, and it's been a real little workhorse. And I'll be very, very sad if this turns out to be very, very messy. But it runs on 4 bands, 3.5, 7 megs, 10 megs and 14 megs. So we'll give it a crack. And here it is already pulling in the DX on the 20 meter band. There's a couple of US stations already appearing 20 meters. It's just an absolutely wonderful transceiver. So if you get a chance, great little build too. Bit challenging, but fun build. Have the QDX hooked up. We're on the, we're going to tune to the 3.5 meg band and hit tune and see what happens. So 3.5, and let's just have a look at what it's giving us. Okay, Delta 1. Delta 2 is minus 53 dB. So minus 53, that reads well for me. Okay, time to test the 40 meter band. We have set the stop frequency to 40 megs, not 30. I just want to get a little bit further. And we will hit tune and we'll have a look at what is happening. Okay. Very clean. We have our fundamental 7.019 and bugger all else. So clean on 40 meters. Okay, I'm going to do the 10 meg band. We'll leave it at, we'll get our range to stop frequency to 40. It seems to be on 90 for some reason. Okay, it stops 40. We're going to go back to measure and harmonic, and we're going to set it to 10 megs. It should be more precise, but hey, close enough. Close enough is good enough. And we'll just hit tune and see what 10 megs looks like. Let's set it, the actual frequency measure to 10.136 because that's what it is. Okay, we've set the frequency to 10.136 to make it precise. Let's have a look, or more precise. And the difference is 43 dB. So I would say that that's about a little bit less than 6 dB outside the requirement. But having said that, I don't have a resonant antenna for 10, so I'll be running that through a tuner as well. So I would say that more than likely, once I do that, it will be pretty much right. Comment below if you think that's not true. Okay, 14.074 is the frequency that we are going to be measuring. So we'll go measure, harmonic, 14.074 megs. And let's hit the tune and have a look at what our harmonics look like. Okay, third harmonic, 48, 49. Yep, so once again, that's the highest harmonic we're dealing with. And I am confident that that is every bit close enough for my liking. 49 and better, I'm going to say yes. So, Mr. Summers, this rig is clean. I'm confident to use it. Now, I was really disappointed that the Mooncake transmitter, first transmitter that I built, is very, very dirty. Admittedly, it's only 3.5 watts, but no excuses. It's still producing harmonics that are too high. What I'm planning on doing is, because OzQRP seems to provide adequate filtering, I'm going to take my junked DCT 80 meter direct conversion transceiver from OzQRP here, which I managed to blow up, no fault of the actual rig itself, just my total stupidity, working on gear when I shouldn't have been working on it, not feeling very well, a little bit drugged out after having a wisdom tooth pulled, and yeah, managed to fry it completely. But if it works as well as the 40 meter low pass filter, I'm confident that I'll be able to clean up the rig, provided it's just not too overly dirty. I've looked at the component designations on the actual circuit board in the plans, And that is the actual circuit. And I'm going to rob those components off this board. That's why you should never throw anything away. And put the low pass filter as close to the transmitting point as possible so that there's no stray radiation heading off where it shouldn't. And fingers crossed, we clean the Mooncake transmitter up. I love this transmitter. I'm very proud of it. It's very simple, but it's something that's been completely organically created by me, cobbling together so many other people's ideas. But, you know, with creativity sometimes comes some difficulty. So maybe, just maybe, these parts that I've scavenged mostly, I did manage to wreck a couple of capacitors getting them out, but they're the same value that we used in the 80 meter DCT Oz QRP. So hopefully this will clean up the output on my Mooncake homebrew transmitter. Let's pop it in and see. And that is more filtering installed. Will it help? We will find out. So here once again is the setup. We have this cord, BNCs at either end, running into one end of our attenuator. As I said, the attenuator, it says on here, 40 dB attenuator up into the gigs, and then we come down into the RF here. And I'm hoping, I've got this set to 0 to 15, I'm hoping that it behaves itself. Okay, folks, it's time to test to see whether this has worked. I'll give us a little side tone off the TS520 and see what's happening. And as you can see there, all of those harmonics are 50 plus dB down. So I am very happy about that. Obviously, this was built so poorly by me and designed so poorly that it really needed heavy filtering. But by adding that extra stage of filtering, we were fine. So I'd say that the original design that I got, and I'm pretty sure the original design was good too, because it was a Charlie Morris design and thoroughly tested by him. So I would just say that this rig was generating quite heavy harmonics. So we've now got an acceptable rig. It's up close to 2 watts on the power meter that's on the ATU, and I think that's fairly accurate, but probably not as accurate as the other meters. So I'd say, look, we're getting 2 watts, and it's a clean 2 watts, and that makes me a very happy person, because a lot of the time people complain about the noise that's around on the Spectrum, and a lot of that is care of the crud that's being generated by the high-tech electronics that we're using. It's high-tech, but it's generating more noise than it ever has before. And so that's something that's very difficult to avoid, but we're really our own worst enemy if we start building rigs or operating rigs even that we're buying from overseas that are generating these harmonics, because of the nature of the ham bands, which are all harmonics of each other, which makes building antennas and whatnot very easy. But it also means that if we're generating harmonics, quite often those harmonics will be on our own bands and be interfering with other amateurs. So that's another reason, just out of self-interest, that you wouldn't want to be operating crappy gear that generates harmonics. And that's the best case scenario. The worst case scenario is that you interfere with essential services and you get yourself in a whole heap of trouble, and you also cause problems for other people. So enough of me proselytizing about harmonic purity, because as you can see here, I had a rig that was very dirty and I was using it, but we live and we learn. And so I'm happy with that rig now, and I can use it with confidence. I think we'll do one more test, and that is the Puxing PHF UHF 2 meter 70 centimeter handheld. It's a very early Chinese made cheap radio, and this is care of VK2NAP CW Chris. Thank you for lending me this radio, and it was just something that I could have a play with. So we'll chuck it on the Tiny SA, and we'll just have a look at what sort of Toblerone-like waveform it's making. Hey, it might surprise me. It might be really good. Let's check it out. So we have the Tiny SA Ultra set up for a wider bandwidth, and it's going up to 3 gigs. There will be some non-linearity and whatnot. I was actually incorrect. This is not actually a 2 meter and 70 centimeter radio. This is just 70 centimeter radio. So I have it set to about 440 at the center of the band. I better make sure that we've actually got it set up for that frequency for measure harmonic. Let's go 4
39.900. So that's what I've got it on. And let's key down and have a look at how good it is. It'll take a little while to read. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So once it's settled down, we have a second harmonic at minus 28. Keeping in mind that we want our harmonics on the VHF are even more stringent in the LCD, so that is nowhere near okay. But every man and his dog will be out there with these radios, and they're using them, and they haven't bothered to check them. So
I was going to do a spectral purity test on the Hermes Light, and I did do some quick testing, and what I found was that it didn't look like it should, but I think there may be issues with how I have the actual filter board set up in the software. So I certainly have to do a lot more investigation before I decide to start decrying the spectral purity of this device. And I do know of other videos where people have done spectral purity tests and it has been okay. So it may very well be down to my ineptitude at actually setting it up. But watch this space. We will be having a look at that down the track. I am very, very happy that I have tested the rigs that I use. And aside from the Mooncake transceiver, which for most of the time I was using it was 400 milliwatts. Only recently it's got up to 2 or 3 watts. But it was not right, and it is right now. So I'm very happy about that. Thank you for sticking around right to the end of the video. Please comment below whether you found this video informative, whether you think that I've done a lot of things wrong. That's all good. Like I said, we're all here to learn together. 73, and I will see you in the next episode of The Art of Engineering.